Problem 426. So to find the energy of this system, I am going to use the formula where energy density is 1/2 times electric displacement field times electric field. So that means that what I need to do is I need to define this electric displacement field everywhere and this electric field everywhere. So to start, the electric displacement field is actually fairly easy, because the Gauss's law for electric displacement field only looks at free charge. And if we consider the system a spherical conductor that carries a charge Q, that charge Q is free charge. Any other charge, such as the charge induced in the dielectric material, is bound charge, so it doesn't count. Which means I can say from Gauss's law for electric displacement that the electric displacement field is equal to 1/4 pi times Q over R squared. That's not everywhere, that is for everywhere R is greater than A. Second, the relationship between electric field and electric displacement field we can see in equation 4.35. The electric field is 1/epsilon times the displacement field. So this electric field will change and will experience a jump as we hit the bound charge on the surfaces of A and B. We should therefore define electric field as a piecewise function. While we are inside the dielectric material, electric field is given by this formula, and while we're outside the dielectric material, the electric field is given by this formula. So putting them together, electric field is equal to 1/2 times the integral of d dot E d tau. All right, so we have the 1/2, we're going to keep there. D and E both have terms Q over 4 pi. So we have Q squared over 4 pi squared that we've pulled out, those are constants. Both regions of E have a 1/epsilon naught, so I've pulled out an additional epsilon naught. Now within the integral, because we are dealing with a spherically symmetric situation, I have reduced d tau to 4 pi r squared dr. And I've pulled the 4 pi out of each of these integrals. And I've left the r squared there. In addition, this inner portion of the electric field has the 1/1 plus chi e, so I've left that there. Finally, both E and D have a 1/r dependence, so d dot E should be 1/r to the 4th power. That's these terms. Next, I'm going to do a little bit of simplification. I'm going to say that these 4 pi, since they're added together, collectively cancel one of these 4 pi's. And I'm going to distribute this 2 there to become Q squared over 8 pi epsilon naught. And I'm going to cancel some r's here, so r squared over r to the 4th power is just 1/r squared. That gives a slightly simpler statement. Now time to evaluate these integrals. The indefinite integral of 1/r squared is -2/r cubed. So for this first term from b to a, -2/b cubed times 1/1 plus chi e minus -2/a cubed times 1/1 plus chi e. For this integral, we're going from b to infinity, so that's -2/infinity squared, or just 0, minus -2/b cubed, no chi e in this term. Factoring out this -2 and getting rid of this plus 0, we can say that the total energy is given by this formula right here. Now, one more thing I've done just to make this problem a little bit neater is I have pulled out a factor of 1 over 1 plus key e from inside the parentheses, pulled it here, cancels the 1 plus key e here, cancels the 1 plus key e here, and creates a 1 plus key e in the numerator on this term. But 1 plus key e here and minus 1 here, remember this one, we've canceled out this, so these are both over b cubed. We're just left with key e over b cubed plus 1 over a cubed.